Thank you for the invitation to this nice program. I'm really honored to be here with the audience from the real audience and the audience from the Zoom. So I'm really excited about this. And thanks for the previous 2 talks as well. These were also great. So with that, let's begin the talk. The talk is Scalable Trustworthy AI. And apparently I just started a very new group at the University of Tübingen in Germany. It's only a 4-month-old group, and we only have 2 students now. But I guess it's going to grow much faster in the next few months and years. So, right, and I was also previously with Naver AI Lab in South Korea. So now talking about trustworthiness in AI, it's a popular topic in AI field these days, right? And I would like to frame this as a transition from the what question to how question. So what do I mean by that? What I mean by what task is, for example, when you have an image like this and you have a label prediction task based on that. But what I'm trying to say is this is what task, and this is probably not enough in some cases, because, for example, you can have multiple choices for your recognition mechanism. You could be looking at the car body or the road cues for making the prediction for a car, where car body is kind of a causal and robust cue, whereas the road is spurious cue. Right, but there's nothing that stops the model from taking this non-causal spurious cue, which then may cause problems, right? So, for example, if you don't care about how it achieves the recognition, then the model can just look at the background of the image to predict wrong answer, right? In this case, you're not looking at the frog in front and just looking at the road pixels to predict the presence of car here, which is obviously wrong. So now how you solve the problem also matters, and there are close relationship with robustness and explainability issues of AI systems. So now we are seeing some shifted focus in machine learning in general. So now we see a lot of benchmarks in computer vision focusing on the how problem as well. For example, you're looking at test distributions where objects are in different kind of environment where the, for example, you can introduce some kind of blur or noises at test time and try to see how well your model is generalizing to those cases, or you're kind of removing your object from a familiar background to something new. Or in natural language processing as well, you start to look at how your GPT-3 model or your large language model is addressing the problem. You're not just asking for the answer, but you also kind of prompt the language model to think in a chain of thought fashion, so that you also care about how the model is approaching the problem, and that also tends to improve the accuracy of the model solution. So now there is a bit of trend like that, and now we try to conceptualize it a bit in a more simplistic kind of framework. You can think of the whole framework as something like this. You start from an input, and then eventually you want an output, but in the meantime, you wish to have a more kind of nuanced kind of mechanism in between. That could be the cue that you use for making the recognition, or the explanations for the mechanism or reasoning. In short, these are all how aspects that we care about. So you can say machine learning 1.0 was about learning the relationship between X and Y, but now we start to care about the Z variable here as well. But one caveat here is that for machine learning 1.0, you learn the distribution from X, Y data. But since we are just trying to extend what we have been doing to this kind of new problem, we still make use of just X and Y data to predict X, Y, and Z. And that's, I wonder if that's actually really possible, right? So to show how hard this problem is, let's think about a toyish case here. So let's try to learn X, Y, Z from just X and Y. Sorry. So let's say your training data looks like this. You have small red circle, and then you have label 1 for that data, and then you have medium-sized green triangle, and your label is 2, and you have big blue square. I don't know why this is so hard. And that's label 3. And you train a network to predict 1, 2, and 3 for those kind of data. And now you try to generalize your model to this new kind of sample, which is small blue triangle. The problem here is that there are 3 factors playing in the mechanism. And depending on what kind of Q you're looking at, all 3 answers to this small blue triangle are equally likely. So if your prediction is 1, then that means you're focusing on the scale. And if your prediction is 2, then it means you're focusing on the shape. And if the answer is 3, then you're focusing on the color. So it really depends on the Q that you're using for making the prediction. So if you're not telling the model what kind of Q you should be looking at, then the model can just be doing anything. So we can say this is an ill-posed problem, and you need some extra information to address this problem. And I would say a lot of work in this domain these days is making use of X and Y data and trying to expand the performance on the how problem by making better use of XY data. But I tend to believe there's shallow upper bound in this approach. And we should actually be looking into some kind of new types of data like X, Y, and Z to increase the upper bound drastically and eventually improve further. But then obviously collecting such paired data, X, Y, and Z, is often expensive. So the research question here is how to obtain such signal from humans more efficiently. Okay. So that brings us to the table of contents for today. So in the first part, I'm going to talk about Q selection problem, and I'll try to find cheaper source of Z supervision to make this possible. And then in the second part, I focus on the kind of explainable representation of Z. And here the key message is that if you incorporate probabilistic representation of Z, then that tends to help explanation. So there are a lot of content today, so I'll try to squeeze everything in, but let's move in. Okay, so Q selection problem is about searching for cheaper Z supervision to let the model pick the right Q. So here is an example of car versus frog classification. So let's say your training data looks like this. Car is always on the road and frog is always in the swamp. Then as I said, the model can just be looking at the background pixels to make the prediction. And then you have a problem like this. When your background and foreground cues are swapped, decorrelated, then your model stops working. Okay. So one conceptually simple fix in this case is to introduce a Z label for every X. In this case, we are introducing the background class label for every image. So instead of just saying this image is an image of car, you say there is a car and road as well. And in the second image, you can just say, instead of just frog, you also say there is swamp pixels. And then you can later on try to learn a representation which is independent of the bias variable Z here by using, for example, domain adversarial loss or information removal techniques from representations. But that's obviously expensive because you have to collect a lot of annotations. And so we thought about, sorry, an alternative solution, which is to learn debiased representations with biased representations. So I'm just going to go over the high-level idea of this paper. So you start with a your original model looks like this. And you say, if you just train this model on your data, then it's going to be biased. So what you do is you introduce a second model, which is intentionally biased. And then you put a B-difference supervision between the two models. And then the first model, your original model, will learn to be different from this intentionally biased model and get de-biased. So that's basically the idea. And let me give you an idea of how one could do this for, let's say, texture bias for image classification. It is known that image classifiers tend to just look at texture cues for making predictions instead of the global shape cue. In that case, you can introduce a second model, intentionally biased model, which is only capable of looking at small receptive field. So they are just only capable of looking at local texture cues. And your original model is ResNet, so it's in principle capable of looking at shape cues, but simply it chooses not to look at shape cues because you can just rely on very simple texture cues to make the prediction, right? So in this case, when you apply this B-difference supervision between this BACnet, which is just looking at small receptive field, then the ResNet learns that, okay, I should probably not be doing what BACnet is capable of doing, and learns to now expand the receptive field to look at more global cues. The second example is when you have action recognition based on videos. It is known that when you train classifier, let's say 3D convolutional neural network for action classification on videos, it still just looks at static objects. Because, for example, when you say you have canoeing or applying cream activities, you don't really need to look at the movement or complex temporal cues to make the prediction. You can just look at the river cue and the canoe boat cue for canoeing or kayaking. And then you can also just look at the finger or the skin pixels to say, okay, this is an activity about applying cream. So in this case, again, what you do is you introduce, sorry, yeah, I keep coughing, sorry. It's harmless though. I got negative test results, so it's fine. Anyways, you have ensemble of 2D ResNets, for example, and then they are only capable of looking at static cues per frame and not capable of looking at complex temporal cues. And now, if you apply this B-difference supervision, the 3D ResNet learns that it should probably be looking at temporal cues instead of just static pixels, static cues. So you see the pattern here, which is that all this work is about addressing myopic biases or short-sighted models. Another example is when you have a language model, and let's say for a particular data set, if you train a language model on that, it only learns to look at word-level cues instead of the whole reasoning over the whole sentence or paragraph, right? For example, you can just count the number of knots in a sentence or a paragraph to say the overall sentiment is negative or positive, if that's sufficient for solving the problem in the data set. So in that case, again, you can subtract a word embedding, which is only looking at word-level cues, from the global model, like BERT model, to make it attend to more global cues. So the pattern here is that when you have an architecturally global model, but the data itself is only encouraging the model to look at very local and short-sighted kind of way of reasoning, then you can actually, it's often very easy to come up with an architecture which is intentionally myopic, and then you apply this B-difference supervision, and then the first model is then incentivized to utilize more global cues. So that's the basic idea. And here the key point is that you don't actually need to spend money on collecting the Z labels in this case. And you can simply introduce a second model, which is just a downsized or less capable model than the original model. And then you can subtract the second model from the first one. And that's it. Okay, so that was one way to go beyond the cost problem. And then we, for the second kind of approach, we go back to this the example again. And the other way to introduce the Z Q here from humans is to introduce Z as a location variable. So in your training data, you can say your box location for the, you can let the annotators draw boxes to indicate the foreground object in the image. Let's say the annotator is saying the car is here using a box, or the frog is here. And drawing box is not such a bad idea because that's rather cheap, roughly $1 per 100 boxes in general. And you can even speed this up using scribbles and points instead of boxes. But of course, one cannot really ignore the developmental cost for annotation systems. So the question here is, can we even avoid localization supervision at all? And one paper that was kind of going in that direction was this paper, Weakly Supervised Semantic Segmentation Using Out-of-Distribution Data. So yeah, we were talking about Q selection problem, but then we kind of suddenly jumped into this weak supervision problem. So I'm going to kind of explain a bit of connection here. So we framed the problem into via weakly supervised segmentation task, which means you have only training data that consists of images and corresponding global labels. And the task is to segment out the foreground object. That's what weakly supervised segmentation means. And you can treat this segmentation here as the Z variable. So in other words, you wish, in this kind of task, you wish the classifier that you have trained is extracting the right cues for recognition only from the foreground region. If you have such a classifier, then it's easier to extract the object localization information from this classifier, and in turn, that information will be used for generating the segmentation using only the global labels. And right. And here, a lot of issues arise because of the foreground-background correlations. For example, if you have train label, they tend to be correlated highly with the track, the train's rail or track in the image. So if you say, okay, please point out where the train is in the image, then the model tends to say, okay, there seems to be some track here, and that I believe is a train. Why is that? Because in every image that contains a train, there tends to be the train track as well. So you have a lot of typical examples like that, like snowmobile and snow, and skier and snow as well, and you see what I mean, right? And then, so obviously when you have this kind of localization information from humans, then you automatically solve the problem. But again, we're questioning whether we can avoid this annotation cost, right? And so the solution that we propose today is something like this. So we introduce hard negative images instead of introducing localization supervision. So now we introduce a bunch of novel images where there are tracks, the background classes, but you say, okay, there's no train in this case. And these are kind of sufficient information to say which part of the image in the original image was train and which part of it is not a train, but track, okay? So now the question is how to collect such hard negatives for every class. Oh, before that, I actually have more examples. So for this example here, sorry, the hard negative training data looks like this: a road image without a car, and yeah, the swamp image without a frog, right? And you introduce them as examples without the foreground class. So how do you collect such hard negatives? You start from a candidate OOD set. So in this particular paper, we used we had the Pascal weakly supervised semantic segmentation task. So we had open images as a candidate out of distribution set. And then what we did afterwards was to rank all the images using our pre-trained classifier for the class train in this example, and then sort them, right? And then you're going to have a lot of images in your retrieved images that corresponds to high predictions of trained class. And then the next stage is, given this ranking, you threshold it as well. So you're going to remove all the images with the probability less than 0.5. And then after pruning, you do manual filtering with human. So you're going to manually filter out images that actually contain the train. So what remains is a set of images that are highly likely to contain a train class according to a model, but actually not containing any train according to a human. So now we have hard OOD set. And here the question is, okay, if you're going to have to collect a lot of data like that, then that's obviously going to be very expensive. So the other question is, how many per class do you need to see an effect, right? And here I'm measuring kind of the performance in terms of the MIOU score for the weakly supervised semantic segmentation. And by the way, like 1% points or 2% points improvements here is pretty large, because that's that's a very highly competitive benchmark. And here what we saw was that even if you have just one image per class like that, that already improves 2% points MIOU increase. So I would say like just collecting one more image per class is very cheap, and that's a very cheap source of that information. In other words, the model seems to be very hungry for those kind of negative samples, for being more robust and actually figuring out what's the actual foreground region per every image. So if you look at like class-wise breakdown, you see that the classes that are kind of known to have more correlation with the background pixels tend to have more improvements, which is good. So that was about another way to get cheap Z supervision through hard negatives. And now I also like to talk about some of the current work that is not published yet, but still very interesting. So this is an annotation interface for ImageNet. And some of you may know that ImageNet is collected by letting humans click on the images among the candidate set of images that correspond to the class of interest. So in this case, we let the human click on the Bazoon images. Okay. So here I'm interested in annotation byproducts. What do you mean by that? What ImageNet people originally collected out of this interface was just whether annotators have clicked on the image or not. But in this case, I'm also interested in the click locations and the timestamp and the general front-end composition of the images and all kinds of interaction, like human-computer interaction evidence. So eventually, what this leads to is annotation in this kind of format for every image. So I'm bringing up one example here. So the blue part corresponds to the original annotation, which is just telling you whether an image is selected or not. But now I'm on top of that, I'm collecting, for example, the mouse track records and the click records, as well as an anonymized worker ID. Okay, so where am I getting at? So a bit of statistics of ImageNet plus Cocoa annotations. We have re-implemented it using $30,000 US in total. And this is thanks to Neighbors and Professor Jin-Young Song from Digist, their generous funding. And for ImageNet 1K, we have collected about 86.7 training images annotated this way. And Coco 2014 is also annotated almost fully. So we are we are going to open source the paper, code, and data soonish. So the main idea of the paper is that annotation byproducts do not cost extra data, but when you actually use those annotation byproducts for training machine learning models, you actually improve robustness and generalization. So that means there's room for improvement for robustness and generalization almost for free, just by logging all the worker activities during annotation. So that's the advice. When you collect a data set, you should actually collect all the annotation activities, and you probably get a few more points for free. So that was it for the Q selection problem, and now let's move on to the explainable representations problem. So here I'm going to focus on probabilistic representation of Z. I told you everything from here. So probabilities are a common language that humans understand and machines understand, basically. If you think about this example of 30% chance of rain, that's like everyday language for humans. Yeah, I mean, it's probably not super everyday language, but it's something that we tend to understand well compared to, let's say, rain is likely to happen with score 23.9, right? Because that value is not calibrated. So the idea here is that probably for Z, we should be using more calibrated probabilistic representations. And that leads us to this keep calm and improve visual feature attribution paper. What do we mean by attribution method? CAM is an example. Probably many of you know class activation mappings. So you start from an input image, and then you pass that through a model, and you're going to get score map. And afterwards, you're going to have spatial pooling, and you have class label, and yeah, that's the training procedure for general convolution neural networks. But on top of this score map, you can do thresholding to get some foreground, background binary mask, and that's going to be your Z in this case, explaining where the model is looking at to make the prediction. And that's also called class activation mapping in general. So everyone is using it, and even I have been like, not even I, but I have been using it nicely for years. But when you think back about the actual interpretability of CAM values as heat maps, it's not actually as interpretable as we would want, right? So in mathematics, what the CAM is doing is something like this. You train the model using this nice probabilistic framework, using softmax cross entropy. But then afterwards, you do something interesting, which is either to take a min-max normalization on this pre-gap, softmax feature map, or something that is not very intuitive to humans. And if you write this down in English, that's super long-winded and very hard to understand what the pixel-wise contribution actually means, right? So we address this problem by introducing a probabilistic interpretation of the CAM score map, which we write down as Z here. So a bit of notation. So X here means input image, Y here means class label, and Z here means the pixel index in the pixel space, where the Q is actually coming from. So in sentence form, what this graphical model means is you should predict Y from X by looking at the particular pixel Z in the image. And we call this class activation latent mapping. Why latent? Because Z in this case is not observed, and we're going to make use of latent variable models. Okay, so in terms of code level details, the whole framework looks like this. You just have an image, and then you have CNN layer, and then you have some something going on here to result in some kind of final feature map. And on top of that, we have three heads. So one case is when you have the testing phase, or interpretation phase, or training phase. Okay, so the first part is shared by all three phases. So what you do is a bit of normalization everywhere to result in a joint distribution PYZ given X. And that's going to sum to 1 when you pull everything together. So that's a very well calibrated tensor to start with. And then what happens at testing phase is very simple. You just take the global average pooling of all the pixel values, and then you're going to get a global prediction. At interpretation phase, it's also very simple. You just take a slice of the class of interest from this joint distribution, and that's going to give you a score map like this for the particular class of interest. And the training phase is a bit complicated because you're making use of latent variable model. In the marginal likelihood case, it's still very simple because you're taking the global average pooling first, as in the testing phase, and then you're applying the normal negative log likelihood as you train normal CNN classifier, right? Or you could be using expectation maximization framework, where you first generate a pseudo target by normalizing your joint distribution using the ground truth class information, and then you take the pixel-wise negative log likelihood using segmentation loss, okay? And then you're going to train the whole thing in this way. So, as you've seen in the previous slide, the interpretation in this case is super simple. You just take the observations, like you just plug in the observations, and you're going to have your class score map automatically. And in English, it's also very simple. The probability that the Q for recognition was at Z, and the ground truth class Y Y hat was correctly predicted for the image X hat. It's very simple. And what is the actual benefit that comes out of this more interpretable score map? Which is that you can actually do the calculus of the score maps for different classes and so on. So for example, you can combine the score maps for different classes to generate a score map which is focused on a superclass, which in this case is a dog class, right? And previously for CAM, this kind of calculus was not possible at all because the calibration was not done before, right? And you can even subtract the score maps to generate some kind of counterfactual explanations, which is good. Yeah, I'm kind of showing the benefit of CAM over CAM based on the qualitative results here, which is remove and classify. If you know this measure, then you probably understand that lower score here means better, because you don't have to, like, this is telling you that how many percentage of pixels you have to remove according to the score map to have real reduction in the classification score. It's kind of complicated, but here the gist is that lower is better, and it turns out that CAM variants tend to get much better scores than the CAM variant, which is yellow here, right? In all three benchmarks. Well, actually, this CAM ML was performing slightly worse than CAM. Well, yeah, sometimes much worse than CAM in some cases, but overall, it's pretty nice replacement of CAM. So here, again, the disclaimer is that CAM is a great attribution method still, and many people still should be working on it. But the problem is that CAM actually lacks interpretability as one would want. So we have come up with a novel method, CAM, which improves interpretability with more probabilistic interpretation of Z. And yeah, that sounds to be good. And now we move on, and let's talk about something else. Let's talk a bit about metric spaces. So, metric space is a such a nice tool for machine learning, because they encode the semantic similarity very well. So, for example, you have an embedding space like this, and you're trying to embed 2-digit MNIST data set. And you have 17 here and 47 here. And when you have a new sample, like 47, you wonder where to put this sample on in this embedding space. And obviously, according to the semantic similarity, right? So this 47 will be close to 47, and this 17 will be close to 17. And the distance is doing a lot of things here, because the semantic similarity is expressed via the Euclidean distance. Or some people nowadays use other geometries, like hyperbolic or spherical metrics, which are also good. And that's very powerful. You come up with deep metric learning, retrieval systems, representation learning, and these days self-supervised learning as well. But I'm going to tell you what metric spaces cannot do. For example, let's say there's a bit of occlusion in the first digit in this query sample. Are you going to put that near 47 or 17? Because there's a bit of occlusion here, and 17 and 47 are both likely, right? Also, putting such a sample in the middle is not the best idea, because your location in this case means semantic meaning, right? So that is kind of assuming new semantic meaning for this class. Instead, what we want is something like this, right? So if you have a probabilistic representation of every sample, for example, in this case, two mixture of Gaussians. When you have a certain sample, like 17, then you're going to put these two components close to each other. But when you have an uncertain sample with multiple possibilities, then you're distributing your components in different parts of the space. Okay, so in summary, what metric spaces cannot do is to represent the concept of inclusion. They can represent closeness, similarity, very well, but they cannot say one data point is containing the other data point. And I believe there are a lot of rich reward applications for this concept when machine learning kind of embraces this concept in the representations. And for that, we have come up with modeling uncertainty with hatched instance embeddings, where we basically came up with this idea of probabilistic embeddings. And here, you start with a pair of inputs, sorry, pair of inputs, this uncertain one and certain one, and then you're going to have distribution on top of that, and you're going to have your output based on the distributions. But here the caveat is that you're only given the ground truth supervision for X and Y pair without Z ground truth. So you don't have any observation for Z. And so you also, in this case, have to train the Z part of the relationship only through some kind of latent variable method as well. So this is kind of the recipe for training such as that knows the notion of inclusion. So basically, in a nutshell, it's Siamese network with some sampling going on here and here. So you obviously use reparameterization trick, and then you have some k-squared samples, and then you do Monte Carlo integration. And then you have binary cross-entropy loss. So these are kind of complicated, but every component is kind of required to make the network learn the concept of inclusion. So I have a few more slides to explain the concept, but I'm wondering if I have time for that. Yeah, let's skip that part. I'm gonna put this slide on my web page, so you can always come and take a look. So just conclusion here is that when you have, like, I'm comparing ensemble training versus Monte Carlo softmax cross entropy, which we use here, and K diverse training. If you know each of them, then it's kind of obvious to you, but I can explain simply, which is that for every sample, you're gonna have different weights right? So if you just have an ensemble of all the predictions from different samples, then you're treating each sample equally, uniformly. So you're kind of training every member of the ensemble. But when you have k-diverse training, which is the most extreme case, you're not training every k sample in your ensemble, but only the most correct one. So you're only encouraging the most correct member of the ensemble to be correct, even more correct. And that lets the model learn something more diverse. And we're doing somewhere in between. So we're going to put a lot more weight for the samples that are more correct than the others, and less weight for the others. If you train a model like this, then the model learns to assign more uncertainty for uncertain samples, because it's obviously better for the model to kind of diversify the vets for actually uncertain samples. So this is how you increase the inclusivity of the inclusion kind of property for actual ambiguous samples. So if you train a model with those kind of samples, like 3-digit numbers with possibility of occlusions, then you have an embedding space like this. So if you have clean images, then your embedding will be almost like points in rather than Gaussians in the space. But when you have corrupt images like these, then you're going to have a lot more wider Gaussians in the embedding space. And if you look at one of the embeddings more closely, then you're going to see that for those kind of clean samples, 0, 3, these are going to be mapped to a place in the embedding space that's closer to the centroid for 0, 3, which is good. And the Gaussian will be very small. But let's say when you have a very uncertain sample, like 52 here, the ground truth is 52, but if you actually look at the first digit, it's you cannot actually say if it's 5 or 2 or 3 or something, right? So if you look at the Gaussian that corresponds to the sample, you can see that the centroids that are closer to this Gaussian are actually 52, 32, 22, 42, 12, and 72. So these are all kind of likely classes for this sample. In other words, I tend to see this as an evidence that your probabilistic embedding has learned the notion of inclusion, because this ambiguous sample is kind of including all the possibilities that it could be taking, which is good. And one application, more recent application of that was in cross-model retrieval. Why we talk about cross-model retrieval all of a sudden? That's because multimodal representations also require the notion of inclusion in some cases. Because, for example, if you look at this image containing train and platform in a train station, there can be a lot of possibilities to describe the image. And all of these have to be kind of mapped to the same embedding space to enable, let's say, retrieval of sentences based on image or vice versa. So in this case, you also want the query to be kind of included in all the intersection of possible captions in the same embedding space. And in the other way around, also you want your query, text query, to be enclosing all possible image representations in the same space. So that really lets you think about how to encode inclusion in the joint embedding space. So here the solution is quite simple. You just learn the same, you actually use the same method as before, but in a joint fashion for different modalities. And also on CUB dataset, you have caption per image. So if you look at the image samples, you tend to observe narrower Gaussians across the embedding space. And in the same embedding space, you're going to see text examples which are kind of broader in some cases than the images. It's kind of interesting to see how they try to include each other. Okay, so probabilistic representations I have talked about, right? So these are kind of useful tools for kind of communicating with humans what the representation is actually trying to do and so on. So yeah, it's one of the favorite one of my sorry, one of my favorite tools for encoding the Z information. So I'm running into summary. So we are trying to address an ill-posed problem, right? So we have talked about how to get more data from humans and from other sources, but in a cheap way. And we have talked about Q selection for doing that, or explainable representations. So by introducing kind of probabilistic way of representing Z, we kind of automatically have more kind of better framework for containing the Z information. Now let's go to my 5-year interests from now on. Also because I have just built a research group, right? So obviously first one is to better understand humans, how humans achieve recognition. That could include like physics, temporal cues, human bias, uncertainty, etc. I'm also kind of interested in like what are the essence of recognition, like primitive shapes, right? From human psychology. We don't really need to draw the whole details of an object to make it kind of communicate what you mean by the drawing to another human, right? So that kind of extracts the gist of the recognition. So that could be another interesting idea. And obviously, I'm also interested in getting more house signals from humans. So I talked about annotation byproducts, but in this case, we can kind of let the humans wear wearable devices to record the annotator gaze. And yeah, it's interesting to think about different ways to get more information from humans. Or we can ask different questions, more advanced questions to humans instead of just labels. For example, in this case, we are asking humans why they think this label is so, for example. Or yeah, this is the open images localized narratives, and yeah, this is another great example of maximizing the input from humans by prompting them in a different way. And I actually believe evaluation aspect is also very important for this how task, particularly because this is actually another instance of weakly supervised learning task. Because you need to learn X, Y, Z from X and Y data, plus possibly some human guidance. And this is an ill-posed problem in general. And when a problem is ill-posed, then people try to do a lot of different things to make this well-posed again. And there is a lot of issues with fair comparisons and all kinds of issues, right? And for that, I also point to one of my previous tutorials at ECSV 2020. So I have YouTube link here. Again, the slides will be shared on the web, so you can watch them later on. Yeah, I want to move on. Okay. And finally, I'm interested in mathematical tools for representing how as well. So I'm interested in dynamical systems, stochastic processes, machine learning. We had some paper before on that. Causal learning is also very interesting. Making use of external knowledge graph or time series analysis. These are also my interests. So final slide, 5-year research aim is to make it possible that AI makes quantum jump in productivity in humans. And Sundar Pichai once said, advances in AI will be more profound than fire and electricity. I tend to kind of try to share the same viewpoint as he does. So hopefully that happens. So questions? Thank you.